So, hello students. Today is the second session of our chapter that we have started earlier. That is the chemistry of D and the F block elements. And today we will go further a little bit that from where we stopped in the last class. So today mainly we will focus on the metals, their standard electrode potentials, their electronic configurations, their oxidizing ability or reducing ability, and such kind of things. So those will be the main concerns for this session of D and F block elements. So we shall start from the beginning with the question number 1, which is the only 3D metal that is incapable of liberating dihydrogen from acids. So we have a variety of metals in the D block elements. So it starts with the scandium from the left hand side and it ends on the other side as zinc. So meanwhile, we have the metals titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. So these metals are actually intermediate between scandium, which is on the extreme left side of the D block elements, and zinc, that is in the extreme right hand side. And one thing more to point out, all these are 3D metals. So if not specified otherwise, all the metals that we will talk about will be on the 3D series. Okay, because they are most abundant in nature. They have the most, they can be found in the earth's crust in the major amount. That's why these will be discussed much more. So from scandium, if we go to the right hand side, we will reach up to zinc. Now the question is, which among these 3D metals is incapable of liberating hydrogen from acid? So acid is nothing but this AH. If I denote a specific acid, that is AH, which is a Bronsted acid, because this H plus will be liberated. So that's why it is a Bronsted acid. And here we have a transition metal, whom we will denote by Tm. That is the transition metal. Now this transition metal has to react with the acid, and the product will, one of the products will be H2. Now what will happen with the transition metal? Now the transition metal will actually capture this A negative, because you see transition metals are actually positively charged. Because they are metal, they actually are able to subtract the electron. Now if we have this Bronsted acid, which H will be liberated as delta plus, and there is a delta negative charge on the A, that is the conjugate base of this acid. Now among these, you can readily accept the fact that since transition metals are electropositive in nature, so it will attract the opposite pole. So it will subtract, or it will abstract this A minus, not the H. So this A will be actually bonded to transition metal. So the other product of this reaction will be TMA. If it is an hypothetical condition, TMA is an hypothetical compound. So if we have a realistic explanation of the same, I will suggest you to have this with the zinc if it reacts with HCl. Here this A is nothing but Cl. Now what happens here? Here also H2 is eliminated from the reaction mixture, and the other product will be ZnCl2, that is the salt, because the class 2 state of zinc is very much stable. That's why from zinc 0, it will go to zinc plus 2. So this is an oxidation from zinc to zinc plus 2, because zinc is a reducing agent and it reduces the acid, that is HCl. It is H plus, so it has plus 1 charge on itself. So from plus 1, it will be liberating this 0 state H2. So here from HCl to H2, it is the reduction. So from H plus to H2, it is the reduction that we will denote by RED. And from zinc to ZnCl2, we will denote it as oxidation because it is Zn plus 2. So it is actually oxidation. So zinc itself is getting oxidized. That's why zinc is the reducing agent. HCl is getting reduced. So HCl is the oxidizing agent. So between zinc and HCl, this reaction is actually quite feasible. It occurs readily. So whenever we will add an acid to zinc or any such 3D metal, it will readily liberate acid. So what happens in the laboratory actually? So you take zinc metal in a round bottom flask and you add acid drop by drop. We will see this effervescence of molecular dihydrogen will be liberated from the reaction mixture. So that happens and a white colored salt will be readily precipitated out. That is nothing but this ZnCl2, that is zinc chloride salt. So this reaction is quite feasible at room temperature and it occurs readily. But there is a metal that is actually not able to do so, which is copper here. So that is the answer here. The copper has some unique behavior. So among all the 3D metals that you will encounter in this 3D series, from scandium to titanium reaching to zinc, we will see that copper has some unique behavior. It is actually not capable to liberate hydrogen from the acid. So what is the reason behind this kind of observation? So you see the major thing why zinc 0 will go to whether Zn plus 2 or any metal from its 0 state, will it go to the M plus 2 state? That actually tells how this reaction will be feasible or not. This depends upon the reduction potential value of this M plus 2 couple, which we will denote at EM plus 2 0. That is the standard electrode potential. Now, in this case, you will see the standard electrode potential of H plus to H2 is actually assumed to be 0. So this is EH plus, and we have this half mole of H2. So the standard electrode potential value of EH plus H2 is actually taken as the reference. That is 0 volt. That is the standard electrode potential. So whenever this acid will get reduced to molecular dihydrogen, we will take the standard electrode potential value as 0. So that is the reference frame. Now, if a metal is having the reduction potential below this 0, then only it can actually reduce the acid. But if it lies above this 0 value, then it cannot actually reduce the same. So now I will show you a typical graph where you can understand this thing better. So let me draw here for your reference. So if I can take up this section of the page here, and I will actually border it so that I can draw the picture here. So here you have this graph. So in this case, now on the left hand side, that is the y-axis, we will have this standard electrode potential value in the y-axis, and in the x-axis we will have the metal. So the metals will start from their titanium and it will end at zinc, and in the y-axis we will have this kind, and here let's say it is before zinc it is copper, after titanium here it is vanadium, and in the y-axis we have this standard electrode potential value SEP value. All are actually calculated in volt. Now here is the reference of 0, let's say. Now if the reference of 0 is here and it is the line that corresponds to the zero voltage line. Let's say it is 0.5. It is minus 0.5. And you can actually scale up the graph here. And it can be taken as -1. This can be taken as minus 1.5. So this is the typical graph. And in the graph, from titanium to zinc, in all the cases, the E0 value of the metals lie in the below section of the 0 volt. So in case of titanium, let's say it is here. Vanadium, it's here. In case of manganese, it is here. In case of iron, it is here. In case of zinc, it is here. But in case of copper, the situation actually is completely different. In case of copper, if the copper situation is here, in case of copper, the value actually is in this plus 0.34 volt, which is actually here. So in case of copper, the situation is actually gets reversed. This is the position of the copper in the standard electrode potential series. So you can see here, if we have the standard electrode potential value in the y-axis and the 3D metals are in the x-axis. So here all the 3D metals have their E0 value, that is the M2 plus M standard electrode potential value, are below this zero voltage average line. But in case of copper, the value is actually positive, that is more than this 0 volt, which is plus 0.34, which is unique in the entire 3D series. No other metal shows this anomaly. Now, here is the fact that I have explained with you. But what is the main reason behind it? The reason is actually written here. That is the high energy that is required to transform the copper solid to copper 2 plus aqueous is not balanced by the hydration enthalpy. So what happens here? So you have to actually oxidize the metal from the 0 state to +2 state. Now you all know the in the electronic configuration of copper is 3d9 4s2. And if it goes to the copper 2 plus, it will remain as 3d9. Now you see 3d9 is such an electronic configuration where there is no such stability. In the metallic copper form, it was actually stable because it had this fulfilled s orbital. And you know the fulfilled electronic configuration orbitals are very stable in nature. But in this case, when it loses these two electrons, it will go to the 3d9 4s0 configuration. In this case, you can see it is copper 2. And its copper 2 is actually lacking the stability of the s orbital. That's why copper does not want to go to the copper 2 plus state. Even the hydration enthalpy that is actually gained by the copper 2 plus cation is not actually sufficient enough to overcome this destabilization due to loss of the 4s electrons. That's why copper 0 to copper 2 plus transformation needs kind of energy. It requires some kind of energy in the context of this voltage, which is plus 0.34 volt. That's why copper solid is actually reluctant to go to copper 2 plus aqueous. This high energy that is required is not sufficient enough. It's not balanced by this hydration enthalpy. That's why copper is the only metal, that is the 3D metal concerned, that is actually incapable to liberate hydrogen from the acid. Now, with this knowledge in our mind, we will go to the next section. So let me delete this thing. Okay. So let's come to the next question. So next question is, give 2 examples of acid with which copper actually reacts. So we have known the fact that copper is actually incapable of liberating H2 from the acids. But is it everything, or is it all, or is it the point where we will stop discussion? No, because there are some cases every rule in chemistry has some kind of anomaly or has some kind of exception. So those have to be remembered very well. So here also an exception occurs. So where copper actually reacts with the acid. So what are the acids? So the acids which are actually oxidizing in nature, which has some kind of oxidizing power, they are actually able to overcome the destabilization that comes from this copper 0 to copper 2 plus. So these two acids are, first one is the nitric acid. You see nitric acid, the nitrogen oxidation state is +5. And in hot concentrated sulfuric acid, the oxidation state of the sulfur is +6. Now you know where the central atom will reside in its top oxidation state, then it will act as an oxidizing agent. So let's actually learn this thing a bit well. Let's say here we have this 0 state and here we have this +10 state. Now we have this axis. Now in this axis, the compound which is actually sitting in the top oxidation state, suppose the compound here is A. It is in the topmost oxidation state, that is +10. Now since it is in the topmost oxidation state, now this will actually be already, this oxidation state cannot go up because it is the most oxidation state that is cannot be achieved, above which it cannot achieve. So it will readily come beyond it. So if it comes to either +9 or +8 or any such number, so it will get actually it is actually getting reduced. So it is an oxidizing agent. Since the molecule which in the top oxidation state will actually be come down because it has no scope to go beyond that. So it will be the oxidizing agent. It has only one option to come down. That's why it is an oxidizing agent. And suppose an element here, which is B, is in its lowest oxidation state, that is 0. Now it cannot go beyond 0. So it cannot go to the negative version, that is -1, -2 cannot be achieved. So it will go to either +2 or +3. So it itself is getting oxidized. So it is a reducing agent. So this is kind of a trick for you guys to remember how we can say a species is oxidizing or reducing. So if the species in its topmost oxidation state, it will act as an oxidizing agent. And if it is low oxidation state, then it will act as a reducing agent. Now let's come to our question. The question was which kind of acids with which copper will actually react. Now, you know the nitrogen actually falls under the group 15 and sulfur falls under group 16. And the topmost oxidation state of group 15 elements is +5 and the topmost oxidation state of the group 16 elements is +6. So HNO3 nitrogen in its highest oxidation state. In sulfuric acid also the oxidation state of sulfur is the most. So in both the cases, the acids are in their highest oxidation states. So both of them will act as an oxidant. So these strong oxidizing agents will actually react with this reducing agent, that is copper 0, and they will liberate hydrogen. So these are the only two acids with which copper actually reacts to liberate hydrogen. Okay, so now let's come to the next question. Why is chromium 2 plus a reducing agent and Mn3 plus is an oxidizing agent when both of them possess this D4 configuration? Now this question is actually very much conceptual and you have to understand this thing from the very basics. So the question is actually quite simple and it is quite intriguing too. We have this chromium 2 system, which is actually D4. We have this manganese 3 system also, which is also D4. Both of these species have same electronic configuration. Both manganese 3 and chromium 2. Both are actually D4 in nature, but their tendency to react is just the opposite. Manganese 3 wants to go to manganese 2, which is D5. So it actually from manganese 3, it actually accepts this electron. Let me actually correct this line here because it actually shows this transformation. So you have to take another example here. So both of these are actually equivalent. Chromium 3 is equivalent to D4. Manganese 3 is also equivalent to D4. Now manganese 3 wants to go to Mn2. So it actually accepts one electron in its d orbital. So if it is accepting one electron, so it is an oxidizing agent. The case for chromium is a bit different, actually completely reverse, because chromium 2 wants to go to chromium 3. So it actually releases one electron. That's why it is the reducing agent. So its configuration is D3. Now from chromium 2, it goes to the chromium 3. So from same stoppage, it wants to go to the D3. So it actually wants to lose one electron. But manganese 3 wants to accept one electron. That is D5. So in this case, what is the driving force behind this reaction? If from D4 it can go to D5, then you can understand this thing very well. Because you know D5 is the half-filled electronic configuration. And I have told multiple times while teaching you about this D and F block elements that half-filled or full-filled orbitals provide some extra stability to the system. That's why Mn3 wants to go to Mn2 very fast because it wants to gain this half-filled stability that is arising from its electron. So here we have this d orbital. So 5 d orbitals are here and we have this d5 configuration, which is actually stable. But what happens in the case of chromium? So in case of chromium, the situation is a bit different. So in case of chromium, it wants to go to the D3. Now you will say, like we have this D3 configuration. What is the actually reason behind the stability of this D3 configuration? So that's where the case of the crystal field stabilization energy comes into picture. That is nothing but CFSE. So about this specific term, I will talk more or details in the later classes. So for this class, we have to know that CFSE of D3 is actually quite high. That is the crystal field stabilization energy. So on a brief, I will tell you what happens here. In case of d orbitals, you can see the 5 d orbitals are here, but all the d orbitals here are actually degenerate because all their energies are same. So same energy species are called the degenerate species. But in case of the metal complex formation or in case of the compound formation, all the d orbitals are actually not the same in energies. They actually vary in energies. So their degeneracy is actually gone. So here in this case, these 5 d orbitals are splitted between 2 and 3 d orbitals. The lower d orbitals are called the T2g orbitals and upper d orbitals are called the EG orbitals. Now in this case, when we will fill up the electrons, the D3 configuration, so we had these 5 orbitals here. So among 5 orbitals, some has 2 has gone, has come down. Now we have these 3 electrons here. So 3 electrons will be put up like this: 1, 2, and 3. And you say, see in this case, the T2G3 configuration is attained. Now this T2G3 configuration is actually half filled because you see here in this case 3 orbitals are there. So at most it can accommodate 6 electrons. And we have 2 orbitals here where at most we can attain 4 electrons. So this is 3 T2G3 T to the 3 is actually half of 6. That's why T to the 3 is the stable half-filled electronic configuration. That's why chromium 2 is actually ready to go to this T to the 3 configuration. That's why it is a very strong reducing agent, because it actually, from Eg orbital, it actually releases one electron and takes up this T2G3 configuration. But in case of manganese 3, when it was D4, it actually takes up another electron. Because you can see here why it is the anomaly. You see the manganese 3 and this chromium 2. The charge density of manganese 3 is much higher than that of chromium 2, because we are going from left to right in the segment. So from titanium, we are going to zinc. So chromium is here. On the right hand side of the chromium, it is manganese. So the size of manganese is actually smaller than that of chromium, because you know in the d orbital, from going through the period from left to right, because of the poor shielding of the d orbital electrons, the size actually decreases of the metals. Now you can see the manganese size is actually less than that of chromium, and also the charge of manganese is higher than that of chromium, because it is manganese 3 and it is chromium 2. So the charge density, the nuclear charge density of manganese is also high. That's why manganese 3 will readily take up one electron, because it has higher positive charge. But in case of chromium, because it has lower charge density, it will release the electron and it will go to the stable D3 configuration. But the same will not be applicable for manganese. Manganese 3 will actually take up the electron to make this D5 half-filled stable configuration. So that is the reason why, despite having the same electronic configuration, that is D4, chromium 2 is a reducing agent, but manganese 3 is a very strong oxidizing agent. Now we shall move to the next question. The next question is, account for the high negative E negative values for manganese and zinc. For manganese, it is minus 1.18 volt. And for zinc, it is minus 0.76 volt with respect to other 3D elements. Now, this question is actually quite simple to answer. So you just have to look at the electronic configuration of these two elements. First one, let's say, which is the Mn0. So from Mn0, if it goes to Mn2, here it is Mn2, so it is having D5 configuration. You know this D5 configuration is the half-filled configuration, and half-filled configurations are very much stable in nature. That's why Mn0 is actually, Mn2 plus is actually very much stable. So that's why from stable configuration, it does not want to come down to the Mn0 configuration. That is the 3D5 4s2 configuration, or you can say 3D6 4s1 configuration. So Mn2 is reluctant to come to the lower value, that is Mn0. In case of Zn, it is actually Zn2 plus is actually D10 configuration, which is actually completely filled. That's why in this case also, it does not want to break down its stable D10, that is the fulfilled electronic configuration. So in both the cases, because they are D5 and D10, both are very stable electronic configuration, they do not want to come down to their metallic state. That's why they have this high negative E0 values. In manganese, it is minus 1.2. In case of zinc, it is almost minus 0.8. So account for the low value of E negative, that is M3 plus and M2 plus for scandium and Fe. So here also the electronic configuration is actually the key to answer such question. So whenever you will be asked such question, your approach will come through the path of the electronic configuration. So here the E0 value is demanded as E negative, M3 plus, M2 plus. So the questions are pointing towards two metals. First one is the scandium, which is the very fast 3D metal from the left hand side, and the middle one, that is the Fe. So M3 plus, M2 plus E negative values are actually required here. First one is the scandium 3 plus. Now you know scandium is having electronic configuration because it is the first metal, so it is actually 4s2 3d1. So if all the electrons are gone from and before that it has a noble gas configuration. So if all the electrons are gone from the +3 state, so it will come to the noble gas configuration only. So scandium 3 is left with this noble gas configuration, because scandium 0 is noble gas followed by 4s2 3d1. And in case of iron 3, you know iron 3 is a D5 system. So here also you can see scandium 3 has a very stable noble gas electronic configuration, and iron 3 is also having a half-filled D5 electronic configuration. So both these configurations are very much stable. So that's why both of these cations don't want to come down to their lower oxidation state. First one is the scandium 2 and the next one is the Fe2, because they are actually electronical configuration stability will be lost. That's why in both the cases, scandium and Fe, there is very low M2 plus, M3 plus electronic reduction potential value. The next question is, despite having a more stable configuration, copper 1 disproportionates in aqueous solution. Explain. So firstly, we have to start with the copper 0. So copper 0 has this electronic configuration as 3d9 4s2. Or you can say it is actually both the electrons will be actually accommodated, both the electrons should be in their half-filled and full-filled state. So later it actually just had 3d10 4s1. This configuration is more stable than this one because it has this full-filled 3D shell and this half-filled 4s shell. But in this case, it has the full-filled 4s shell, but there is no such case half-filled or full-filled stabilization from the D9 configuration. Now copper 1 is D10. So this one is copper 0, and if we go to copper 1 is D10 and copper 2 is D9. Now this 3D10 configuration is much more stable than the D9 configuration because it is a full-filled subshell, but this is not either full-filled nor half-filled or nothing. So no such stability should actually come from the D9 configuration, but there is significant configurational stability from the copper 1. The question is, though copper 1 has this extra stabilization configuration, though it disproportionates in aqueous solution to copper 2 and copper 1. So first of all, what is this disproportionation? Disproportionation or dismutation is such kind of a reaction where a single species will actually get oxidized in some section and it will get reduced to some another section. That is actually the disproportionation reaction. So let us actually discuss the disproportionation reaction with a typical example of H2O2, which is nothing but hydrogen peroxide. Now hydrogen peroxide is a very reactive molecule and it actually disproportionates at ambient temperature to water and oxygen. Now I have told in disproportionation reaction, a single species will actually get oxidized and others and that very species will get reduced. So in this case, the situation can be actually explained here. So let us balance the equations first. 2 moles of H2O2 that I have divided into 2 moles of separate H2O2 to show which one is getting reduced and which one is getting oxidized and produces 1 mole of oxygen. Now you can see in case of H2O2, the oxidation state of oxygen is -1. But in water, the oxidation state of oxygen is -2. And in case of molecular dioxygen, the oxygen state is 0. So you see in this case from -1, if it is going to 0. So the oxidation state is actually increasing. So it is getting oxidized. So it is actually ox. And what happens to the other molecule of H2O2? The other molecule of H2O2 from -1, it goes to -2. So it is actually getting reduced because the oxidation state is actually decreasing here. So one molecule of H2O2 gets oxidized to O2. The other molecule of H2O2 gets reduced to H2O. So that is the major definition of this disproportionation reaction. So in disproportionation reaction, one single molecule will get oxidized and that same molecule will get reduced in 2 different cycles. So that is the disproportionation reaction. Now what happens in this case of copper? So in case of copper also, you can see the similar thing is happening. You can see here copper 1 is here, which is in +1 oxidation state. So one molecule of +1 copper is actually going to the 0. It is copper 0 because it is metallic copper. So it is getting reduced to copper 0. And another copper 1 is actually getting oxidized to copper +2. So this one is the reduction. And this one is the oxidation. That's why it is termed as the disproportionation reaction. Copper 1 is actually oxidized to copper +2 in aqueous solution, and the other copper 1 is actually getting reduced to copper 0. Now, what is the reason behind such a disproportionation reaction? Though we know copper 1 is having a very stable D10 electronic configuration, still it chooses to disproportionate. So what is the main reason behind it? So first of all, copper plus is okay. Now let's now talk about the ionic potential value. That is the delta hydration energy. Now it is the value of 5. So when I taught you about the S block and the P block elements, mainly about the S block elements, I taught you about this phi sign, which comes from the Fajans rule. So what actually is told by the Fajans rule? So Fajans rule tells if a molecule is cation is having an ionic potential, and this ionic potential, that is phi, can be denoted by the cationic charge, whether is charged by the radius. Since cations are actually here talked about or discussed, so I will omit the negative sign. So it is mainly the charge by the radius. Now let's talk about this copper 1 and copper 2. You have this copper 1 and we have this copper 2. Now which one is having the greater phi? Since the charge of copper 2 is greater than the charge of copper 1, and since the charge of copper 2 is high, then the nucleus will actually show extra power to the electronic environment. That's why the electrons will be dragged more. That's why the size of copper 2 is actually smaller than that of copper 1. So if we say the charge of copper 2 is high, and also the radius is copper 2 is low. But when we are coming to copper 1, the charge is actually less, the radius is actually also higher. So that's why in this case you will see that it's a fraction. And if the numerator is actually increased in case of copper 2 and the denominator is actually decreased. So that's why the phi value of copper 2 is higher. But in case of copper 1, the numerator value is dropped and the radius is also increased. So the value of this fraction is less. That's why if we consider phi of copper 2, it is much higher than phi of copper 1. So the ionic potential value, of copper 2 plus is much higher than that of copper plus. So if the ionic potential value of copper 2 is higher than that of copper 1, then the hydration enthalpy of copper 2 will always be greater than copper 1. So the hydration enthalpy or the enthalpy or the energy required for hydration of copper 2 is much more. So when we are talked about it, so the second electronic ionization enthalpy. So from copper 1, we have to go to copper 2. That requires the second ionization energy, that is IE2. So we are talking about this IE2 actually. This IE2 value is overcome by this hydration enthalpy of copper 2. That's why despite having a less stable electronic configuration, the copper 2 is stable. That's why the reaction goes from the left hand side to the right hand side. And also we are reaching to copper 0 also, because copper 0 is having again the 4s1 3d9 configuration, which is also stable because it has 4s2 3d9, because it also has the 2 4s electrons are fulfilled. So that stability also comes into picture. So that's why, because of the hydration enthalpy of this copper 2 plus is higher than that of copper plus 1, and because there is some stability provided by the metallic copper in terms of its electronic configuration, so copper plus 1 readily disproportionates into copper 1 and copper 2. So with this detailed explanation of this copper 1 and copper 2, I hope you will be able to answer such questions in the later phases also, where we will see the molecule or ion in a high oxidation state will always have some greater amount of hydration enthalpy or hydration energy than the cation in its lower oxidation state. The next question is, comment on the following statement. The transition metal fluorides are unstable in the lower oxidation state. The fluorides are actually small and hard anions. So if we talk about this fluorine, I have told you the fluorine is actually lying in the right hand side in the period. And if you see from the left hand side to the right hand side in a periodic table, the size actually decreases. So the size of actually radius of fluorine is actually less. And you all know the electronegativity of fluorine is very much high. It is among the most in the periodic table. So these three qualities are actually attributed to this fluorine atom. Now here one principle is actually stated, that is the SHAP principle, the HSAB principle. So some actually denote this principle as SHAB principle, or you can denote it as the HSAB principle. So it actually is denoted in the abbreviated format, and its full name is either soft hard acid base or hard soft acid base. So which are actually soft and which are actually hard. So when the center is actually smaller in size, when the radius is actually small and the charge is actually high, then it is a hard species. And when this species radius will be high and the charge will be less, then it is a soft species. Now, according to this hard soft acid base principle, that is the HSAB principle, hard and soft interactions are very much favorable. So they say a hard will actually prefer one hard center, and a soft species will always prefer another soft center. So in this case, what is the analogy? So in this case, we are talking about the fluorides. So F minus ions are actually discussed. Now you see, when the question is as transition metal fluorides are unstable in a low oxidation state. So I have told, like, when the charge is small, charge is lowered, and in this case it is a soft species. So low oxidation species are small. So low oxidation state species are actually soft. And if you can take the high oxidation state species, they are actually hard. Now you see here, I have talked about the low oxidation state species. So they are soft, but fluorine, you see here the radius is small, the electronegativity is high. That's why fluorine is hard. So low oxidation state is soft, but fluorine is actually hard. Now I have told soft and the hard interactions are very much welcome. That's why it is a soft-hard combination. That's why it is not good. That's why transition metal fluorides are unstable in the low oxidation state, because the combination provided by this duo is not quite good. One is soft, another is hard. The low oxidation state metals are actually soft and fluorine is actually hard. And so the fluorines are actually stabilized by the high oxidation state hard metal centers. That is actually written here. So the high oxidation state hard metal centers will be actually stabilized by the fluorides. That's why you see in this case it is vanadium pentafluoride, which is having an oxidation state +5, or chromium hexafluoride, which is having the oxidation state of +6. So these high oxidation state metals are hard in nature. Fluorine is also hard in nature. That's why this hard combination is very much welcome according to the HSAB principle or SHAP principle. That's why we can say that the statement transition metal fluorides are unstable in the low oxidation state is actually correct. Explain why MnF7 is unstable whereas Mn2O7 is quite stable. So in both the cases, you can see both the cases manganese is in its highest oxidation state, that is +7. Here also in manganese septafluoride, it is Mn +7. And here also in case of manganese oxide, that is Mn2O7, the oxidation state are +7. But though F minus or the fluorides of manganese is actually unstable, it is not found or very much reactive, but the corresponding Mn2O7 is a stable molecule. So here comes some points that I will discuss one by one. The first one is the oxygen is able to stabilize the highest oxidation states of the elements via oxide formation. You see, oxygen or oxide ion is O2 minus, but F is F minus. So F minus can only form sigma bond, but O2 minus can form sigma bond as well as pi bond with the metal center. So that's why with the metal center, metal actually prefers this oxide anion over the fluoride anions, because with oxygen, it can form a very strong electronegatively different polar sigma bond, and also by a sidewise overlap, it can form a pi bond. But since in case of fluorine, only one bonding orbital is present, one set of electrons are present, that's why only sigma bond can be formed with the fluoride anion. That's why metals actually prefer oxygen over fluorine to stabilize their highest oxidation states. So there are typical examples where these oxocations are actually found. First one is a VO2 plus, where vanadium is in its +5 oxidation state. VO2 plus, where vanadium is in its +4 oxidation state. TiO2 plus, but titanium is also in its +4 oxidation state. So these high oxidation states are actually stabilized by this oxocation species. Now the ability of oxygen to form multiple bonds, that is sigma bond and pi bond with the metal center, exceeds that of the fluorine that I have discussed just now. Since oxygen have this O2 minus negative charge, so it can actually form sigma and pi bond with the metal centers, which is not possible in case of fluorides. That's why in case of manganese, it can go till Mn+4. So MnF4 is the highest Mn fluoride, but Mn2O7, that is the Mn+7, is the highest oxidation state oxide of manganese. But the actual reason is another one. There is some severe steric hindrance between all the lone pair of F atoms in MnF7. So you can see here is the Mn, and we have these 7 fluorine atoms bound to this Mn. Now you know all the halogens carry 3 lone pairs. So we have here 7 fluorine atoms. So 7 fluorine atoms will be surrounding this manganese +7 center. You all know that is a metal fluorine bond is very much short because the bond length is short. That's why all the lone pair of electrons will be here. And since fluorine atom is also small in size, all these lone pair of electrons will cause severe steric hindrance among these fluorine atoms. This lone pair repulsion will actually destabilize the entire system. Since the atoms are smaller in size, they will be dragged more towards the manganese center. So that will cause a severe steric hindrance. Steric hindrance is, so there occurs severe steric hindrance between these lone pairs of the 7 fluorine atoms. That's why in case of MnF7, the system is actually getting destabilized, which is not that much prominent in case of the oxide species. That's why MnF7 is unstable. The next question is, why is the E negative value of Mn3 Mn2 couple much more positive than that for the chromium 3 chromium 2 or the Fe3 Fe2 couple? So in this case, the much larger IE3 value is the main possible responsible for such observation. You can see is the Mn3 Mn2 couple E0 value. So here you can see from Mn2, if we have to go to Mn3, so Mn2 is D5 and Mn3 is D4. So now D5 to D4 translation will be very much poor, because we have to break the half field stable configuration and we have to go to a less stable D4 configuration. That is actually not in the favor of the Mn2 Mn3 duo. But what happens in case of chromium 2 to chromium 3? Chromium 2 is D4. If it goes to D3, then it will have a T2G3 configuration, which is quite stable. And in case of Fe2 to Fe3, Fe2 is D6 and Fe3 is D5. So it will also have the D5 configuration, which is also quite stable. So in this case, manganese to manganese 3 couple, the much larger third ionization enthalpy value, because it is the transformation from D5 to D4, is mainly the culprit behind this observation. The last question is, how many MnO-Mn bridges is or are there in Mn2O7? This is a very basic informative question that is frequently asked in the exam. So this is a structure of Mn2O7. I am drawing it for your reference. So here we are having 2 Mn centers, and all the Mns, each Mn center is bonded with 3 oxide species. So this will be also bonded to these 3 oxygen. So we are actually reaching at the point of Mn2O6. So the molecule has formula Mn2O7. So we have another oxygen atom in the middle. So that is actually a bridging between the 2 Mn centers. So that is the structure of Mn2O7. So that's why there is one M1O-Mn bridge in the molecule. So with this, we have come to the end of this session. So in the next session, we will talk about the different crystal field stabilization energies, and we shall briefly move towards the F block elements.